accumulator register or AX. So, we will look into these registers that we have in this execution unit. The first one is the accumulator register. As I said that it can be considered to be two 8-bit registers AL and AH, and they can be combined together and used as a 16-bit register AX. AL, it contains the lower order byte and AH contains the higher order byte. So, AL is the lower order one, AH is the higher order one. The IO instructions use that AX or AL for inputting or outputting out 16 or 8-bit data to or from the IO port. So, you can have 16-bit IO port, you can have 8-bit IO port. So, if you are having 8-bit IO ports, then you have to use this AL or AH, the AL register for outputting the value, and if you are outputting a 16-bit value, then the AX register can be used. So, if you are so the instruction itself will be identifying the thing, like if you say in AX some port number should be there. So, if you are reading from this port address, so this is assumed that this will be a 16-bit port and the 16-bit value will come to the AX register. If this is an 8-bit port, then you can write in a similar fashion in AL comma some and again the port address, and this port is assumed to be 8-bit port and the 8-bit value will be coming to the AL register. So, this way we can have both 8-bit and 16-bit access for this AH and AX register. Then multiplication and division also use the AX or AL. So, they can also use this AX or AL register. So, for 16-bit multiplication, so it will be AX register, for 8-bit multiplication we will have AL register. Another register BX. So, BX is a general purpose register, but it has got some other functionality also for the memory addressing. That is why, so this is called the base register. So, again it consists of two 8-bit registers BL and BH. So, they can be combined together as a 16-bit pair into a BX register. The BL is the lower order byte, BH is the higher order byte. So, this is the only general purpose register whose contents can be used for addressing the 8086 memory. So, you can use this BX register as something like a pointer. Okay. So, you can use it as a address for addressing this memory. So, all references utilizing this register content for addressing use DS as the default segment register. So, you can have instructions like say move, can have instructions like move AX comma within bracket BX. So, the meaning of this instruction will be something like this, that AX register will get the content of memory location DS colon BX. Okay. So, DS colon BX. So, DS into the, so this is DS 16 into DS plus BX. So, that way it will come. So, it will be having this 16. So, this BX register is the only register that can be used for only general purpose register that can be used for memory addressing, and this is it is called based addressing. We will see, and in based addressing this will be utilized, and this will be using the DS register as the segment register. Next, we will be looking into the CX register. Now, you see that each of these registers apart from AX, which is accumulator, so other registers BX, CX, so they have been given some special names. Okay. Unlike say 8085 where we have got this ABCD like that. So, it is not that way. So, these ABCDs were a bit arbitrary, but here it is not so. Here this CX register is another 16-bit register consisting of two 8-bit registers CL and CH. CL contains the higher order lower order byte, CH contains higher order byte. Then we have got a number of special instructions like shift, rotate, loop, etc., where the CX register is used as a counter. So, actually a typical example can be of this loop instruction. You see that while using a loop, like say if I want to have a loop. So, I can suppose in high level language we have got a loop like this for I equal to 1 to 10. Okay. So, this body of the loop will be repeated end. If this is the loop, so in case of assembly, when I convert it into assembly level program for 8086, what I can do? I can load this CX register with the value 10 by having instructions like say move CX comma hash 10. So, Cx register value has got is having the value 10, and then I can say loop start. So, what it will do? It will repeat a loop body, it will repeat this loop body number of times equal to this 10. So, I do not have to do anything. So, this loop body can be put here. So, it will be repeating this loop body, and we do not have to check this end of loop condition at the end. So, normally if we are writing this program in 8085, so it will be looking something like this, first initializing some register to some register R to 10, and then writing the loop body. Then we have to check before that we have to have some check also. Before that we should have a check that whether R is equal to this R we have to initialize to say 1, then we put a check here whether is R equal to 10, and if not then I should have the body here, and then I have to again increment R equal to R plus 1, and then jump to this position again. See, this is say L1. So, I have to jump to L1. So, the program will look something like this, the structurally it will look something like this. Now, you see these extra things need not be done in case of 8086 loop instruction. So, these things will not be required, and the Cx register. So, this will hold the iteration count, how many times this loop body will be executed. So, that count is kept in the Cx register. So, I will come back to this instruction when we go to this 8086 instruction set. So, this loop start. So, this will automatically decrement Cx register by 1 without affecting flags, and we will check if Cx becomes equal to 0. If 0, then the 8086, if it is 0, 8086 executes the next instruction, otherwise 8086 will branches to the label start. So, at the end of the loop body, so you can just say loop start. So, it will be jumping back to the loops the label start if Cx is non-zero, and if Cx is 0, then the loop body is over. So, it will be automatically going to the next instruction. So, we can use it for writing something called zero overhead looping. So, there is no extra overhead that we have to pay for this looping purpose. Then another register is the dx register or data register, and this has got again DL and DH, two 8-bit registers. So, when combined with DL, this DL register will contain the lower order byte, and DH register will contain the higher order byte. Now, used to hold the high 16-bit result in 16 cross 16 multiplication. So, if you do 16 cross 16 multiplication, the result will be 32-bit, and for that 32-bit result, this dx register will hold the higher order byte, and this AX register will hold the lower order byte for the multiplication instruction. Similarly, if you are doing the division operation, this high 16-bit dividend before 32 by 16 division, and the 16-bit remainder after division. So, this dx register, so this is particularly suitable for this multiplication and division operation. So, dx register, so for multiplication, so dx will have this higher order 16-bit, higher 16 bits, and your AX will have the lower 16 bits. And for division, so we are going to divide a 32-bit data by a 16-bit data. So, this high 16-bit dividend before this 32 by 16. So, this dx register will have this this high order 16 bits of the dividend, higher order 16 bits of the dividend, and this lower order 16 bits will be in the AX register. This will have the lower order dividend, and the after division this dx register will contain the remainder. So, then the division will be done, and then the dx register will have the remainder, and this AX register will have the quotient. AX will have the quotient, and dx will have the AX will have the quotient, and dx will have the remainder. So, that way this dx register is useful particularly for multiplication and division operation. Otherwise, you can use it for as a general purpose register of course. So, that is always there, but special function for this multiplication and division operation. Two more special purpose registers, stack pointer and base pointer. So, both of them are uniform in the sense that both of them will access the stack segment. So, any instruction that uses stack pointer or base pointer as an operand will be looking into the stack segment of the memory. So, if you say that move ax comma bp. So, if you have an instruction like move ax comma bp, then it will not look into the data segment, but it will look into the stack segment. Whereas, if you look into the instruction move ax comma within bracket si, so then it will be looking into this it will be using ds register as the segment register. So, it will be using the data segment. Whereas, your if you are writing like this, in this case the segment register will be the stack segment. So, this SP and BP they are used for accessing stack segment. SP is used as an offset from the current stack segment register during execution of instructions that involve stack segment in the external memory. So, basically we have got this stack segment register, and then whenever we are doing this push pop operations, then this stack pointer will be utilized, and the stack pointer will automatically be updated, incremented or decremented due to pop or push instructions. So, when you do a pop, then the stack pointer is incremented, when you do a push, stack pointer is decremented. So, this stack pointer, because this stack pointer will be the stack this SS register will be pointing to say this one, the bottom of this memory where this the stack will be made, and then as you are doing a push operation, the stack pointer is decremented. So, so currently the stack pointer value will be say if you have got this stack segment register here, and memory addresses are decreasing in this direction. Okay. So, memory addresses are decreasing in this direction, and then stack segment register is put to the maximum value, and the stack pointer register is made to be equal to 0. Now, after that whenever we are doing a push, so this value will become -1. So, this value will be decremented by 1. So, you will get it. So, it is accessing it will be getting this location where the value will come in a push instruction. Or if you are doing a pop operation, in that case the stack pointer value will be incremented, say at some point of time maybe the stack is full up to this much, all these locations are full and the stack pointer is pointing to this. Then in that case the stack pointer will be incremented, because after doing this operation the stack pointer should come down. So, stack pointer value should increase. So, it will be doing that. Okay. So, this way we can have this stack pointer and this stack segment accessing the being accessed for this push and pop instructions. And the base pointer, so this is an offset within the current stack segment. So, that can be used for in the based addressing mode. So, as I said that many a time when you are passing parameters etc., then to access parameters in the called procedure, so it is necessary to look into the stack segment, and for this purpose this base pointer can be utilized for going to different parameters that you have passed. So, there are two more registers in the execution unit, special purpose register. One is called source index register SI, another is the destination index register or DI. They are used for indexed addressing. So, as you know that indexed addressing is one of the very popular addressing modes, where this registers can be used as index. So, you have got this DS register pointing to the beginning of the segment and DS colon SI. So, that will be pointing to the particular entry within that segment. So, these SI and DI registers, so they are used for this indexing purpose. These instructions that process data strings are use these SI and DI registers together. With the SI will be using DS as a segment register, DI will be using ES as the segment register in order to distinguish between source and destination addresses. So, if you have got if this is if you have got say this as the memory, and then in that memory suppose we have got two segments. So, as I was telling, this is one segment and this is another segment, and you want to transfer a number of bytes from this space to this space. So, this is the so you have got this as the source and this as the destination. There will be number of bytes that you want to transfer. So, what you can do, this segment register you make it to 0.2 by ds, this segment register you make it to 0.2 by es, then the SI register you initialize here and DI register you initialize here, and you can initialize another register CX, the count register, to hold the number of bytes that you want to transfer. Okay. From the source, how many bytes you want to transfer, the number of bytes you can load in the CS register, and then you can use this string instruction moves. There is a string instruction moves. So, if you use this, what it will do, it will automatically transfer the content of these memory locations to this memory location. So, it will transfer, say CA, whatever count has been put into the CX register, so many bytes it will transfer from the source block to the destination block. So, this way this source and destination index registers can be useful for doing the data transfer. Another register that we have is the flag register. So, this flag register, the bits that are important, the bit 0, which is the carry flag. So, this flag is set when there is a carry out of the most significant bit in case of addition or a borrow in case of subtraction. This carry flag is set. This is similar to what we have in 8085 also, the status register, PSW register. So, it is similar to that. Then we have got bit number 1 is unspecified. So, this may be for their internal purpose. Then this bit number 2 is the parity flag. So, this flag is set to 1 if the lower byte of the result contains even number of ones, and for odd number of ones it is set to 0. So, if the number of ones in the lower order byte is even, then it will be 1. So, that is the overall result should be odd parity. So, it following the odd parity principle. Then again the bit 3 is not used. Then we have got this auxiliary carry flag at bit number 4. So, this is set if the carry from the lowest nibble, that is the minimum, the least significant 4 bits that we have. So, bit 3 during addition or borrow for the lowest nibble, that is bit 3 during the subtraction. So, if there is a carry from the lowest nibble, that is the lowest 4 bits, then this bit will be set, or there is a borrow for the lowest 3 bits. So, this bit will be set to 1. Then bit 5 is again of not utilized. Then bit 6 is the 0 flag. So, this is the result of computation or comparison performed by an instruction is 0. If the result is 0, like if you are doing the equality check, or if you are say doing some addition or subtraction operation and the result becomes 0, in that case the 0 flag will be set. Then we have got sign flag SF. So, this flag is set when the result of any computation is negative. The result is negative, in that case this SF flag will be, the sign flag will be set. Then we have got TF flag. So, it is the TARF flag. So, this means that it will be entering into the single step execution mode. So, single step execution, or it is or single stepping. So, this is useful when you are trying to debug a program, like in the initial stage of program development, there may be we write the program, but maybe the program is not giving me the correct result. So, to understand what may be the possible problem, so we need to run the program in a step by step, one instruction at a time, and we can trace through the program to see like how is it going on. So, stopping the program after executing every instruction, so it may be difficult. So, if you set this TF bit, then it will be ensuring that. So, single step execution mode by generating internal interrupts after execution of each instruction. So, after execution of each instruction, it will generate an interrupt that so as a debugger routine. So, we can have that interrupt service routine. So, the interrupt service routine is actually the debugger code that we have. So, now it can access the internal registers depending upon whatever value the user wants to see, they can be shown to the user. So, that way the debugger design can be facilitated by using this TF bit. Then there is IF bit, which is the interrupt flag. So, this causes 8086 to recognize external mask interrupts, and clearing it disables these interrupts. So, basically the maskable interrupts that we have in 8086. So, if you set it to 1, then these maskable interrupts will be reaching the 8086 processor. If you set it to 0, then these interrupts are all disabled. So, there is no interrupt reaching the 8086 processor. Then we have got this direction flag DF. So, this is again for the string manipulation operation. If this bit is 0, the string is processed beginning from the lowest address to the highest address, that is in auto incrementing mode. Otherwise, the string will be processed from highest address towards the lowest address in auto incrementing mode, auto decrementing mode. So, it is like this. So, it is like this, that I want to move this code, like if this is the memory, and we have found that I can transfer the string manipulation instructions. So, they are useful mainly for this transfer of one block of data from one chunk to another. Now, if this chunk are not non overlapping, so this is the segment 1, and from segment 1 I want to transfer it to segment 2. Now, if this segment 1 and segment 2 they are non overlapping, then I can copy this byte here, then the next byte at the next location. So, I can go on doing like this, or I can do the other way also. I can start copying from the bottom, first copy this one here, then copy this one here. So, that is I can do it like this. But if the segments are overlapping in nature, that is in the memory. So, I have got this source segment like this. This is my source segment, or the seg 1 that we have talked about, and this is the destination. Okay. So, this is the destination and this is the source. In that case, we need to move from the bottom, otherwise the content will be overwritten. So, I need to start from the bottom, first copy here, then there, I need to proceed like this. Okay. Or if the overlapping is in the other way, so overlapping is say like this, if this is the source and this is the destination. So, this is your destination and this is the source. If it happens like this, then I have to start copying from the beginning. So, from the first location I have to start copying, from the beginning of source I have to start copying. So, this direction can be controlled by that DF flag in that status register. So, DF flag, if you set it to 0, then it will be copying in one direction, and if you set it to 1, it will be copying in the other direction. So, by looking into these addresses of this source and destination blocks, so you can just figure out like which directions should be set, and depending upon the overlapping pattern. So, we can select the direction. That is the DF flag or direction flag, and there is an overflow flag. So, if this flag is set, if an overflow has occurred, that is if the result of a signed operation is large enough to accommodate in a destination register, then the overflow flag will be 0, and the result is more than 7 bits in size in case of 8 bit signed operation, and more than 15 bits in case of 16 bit signed operation, the overflow will be set. So, it is if overflow. So, like if you in 2's complement number system, you know that if the total space is given as 8 bit, then your number should come from number should be realizable as is minus 2 to the power 7 to plus 2 to the power 7 minus 1. So, if it is not realizable in 7 bits, then there will be an overflow. So, all numbers in 2's complement cannot be represented in 8 bit. Similarly, when you are going for 16 bit representation, it goes up to 2 power minus 2 power 15 to plus 2 power 15 minus 1. So, if you are going beyond that range, then the overflow will be set. So, otherwise the overflow bit is 0. So, this flag register, it will have all these information, and we can use it for different condition checks. So, next we will look into a general. So, this is a summary of these registers that we have in 8086. They can be categorized into 4 groups. Group 1 are the general purpose registers. The general purpose registers can be 16 bit or 8 bit. So, AX, BX, CX, DX, so they are 16 bit register, and ALH, BLBH, CLCH, DLDH, they are 8 bit registers. Then there are 2 pointers, 16 bit pointers, SP stack pointer and BP the base pointer. There are 2 index registers, SI and DI, source index and destination index, they are again 16 bit. Then there is an instruction pointer IP, Okay. So, that is the instruction pointer register that we have. Then there are segment registers CS, DS, SS and ES, code segment, data segment, stack segment and extra segment, they are again 16 bit registers. And then we have got another flag register or PSW, processor status word. So, that is also a 16 bit register. So, these are the registers that we have in 8086 and they have got different purposes. So, this purpose we can summarize like this, that AX register is a 16 bit accumulator register. It has got so we have got also for 8 bit we have got AL that will act as accumulator. So, this the AX will be used for 16 bit operations and AL will be working as accumulator for 8 bit operation. Then the BX register base register BX, this holds the base addressing base value of the base addressing mode, and so therefore based addressing mode we will see. Then the CX is the special function, this is for the count, it is a count register used as count register for holding the count value for shift, rotate, loop instructions. Then the DX register, so this has got this is the data register, apart from working as a general purpose register. So, it has got the special function for holding the multiplication and division operation. During multiplication and division operation, the higher order 8 bit higher order 16 bits will be stored there. Then the stack pointer register SP, so that is used to hold the offset address of top stack memory. So, this stack segment register will be pointing to the bottom and the stack pointer will be pointing to the offset within that. Then we have got the base pointer. So, this is used for getting operands from the stack. Okay. So, this is using the stack segment register as a segment register, and then we can have this accessing within the stack segment by this BP. Then this source index register SI. So, this hold the index value of the source operand for the string instructions, and DI data index or destination index. So, this is for the destination operand for string operation. Next we will look into the addressing modes. So, just like this registers, so addressing modes 8086 supports a good number of addressing modes. Every instruction or program has to operate on a data, and there are different ways in which this source operand can be denoted in instruction. So, this is actually the addressing mode. So, that we know in 8085 also we have seen a number of addressing modes. So, in case of 8086, so we can have different types of addressing, like register addressing, where a register is used as the operand. Then immediate addressing, where the value on which this operation will take place is specified with the instruction itself. Okay. The constant values are specified. Then we have got direct addressing, where we have got this memory address given directly in the instruction. Then register indirect addressing, in which this register will be acting as the address and the register content will be used to access the memory. Then this based addressing, where it is similar, it is particularly useful where for array type of access. So, there is a base address, and with respect to that it will be accessing it, some base registers can be used. Then we have indexed addressing, the SI and DI registers are used for indexing purpose. Then based indexed addressing, where this base and index, so they are combined together for based indexed addressing. Then string addressing is there. Then for port access, so we have got direct IO port addressing and indirect port IO port addressing. And for jump instructions and this call instructions, we have got relative addressing, and we have got so this relative addressing may be relative to the current location, and we have got implied addressing, where the operands need not be specified separately, the operand is implicit in the instruction itself. So, we will see these addressing modes after this. So, in different modes of operation.